Okay, section 10.2 is vectors. So let's take a look at vectors. So a two-dimensional vector. A two-dimensional vector V is an ordered pair of real numbers denoted by the component form as AB with this special bracket that we use for vectors. I think that all this you have seen before. The numbers A and B are the components of the vector V. The standard representation of the vector AB is the arrow from the origin to the point AB. So if there's a point AB and I draw a vector, that is vector AB, starting at the origin. The magnitude or absolute value of V, denoted by the absolute value of V, is the length of the arrow. So this is the magnitude. And the direction of V is the direction in which the arrow is pointing. The vector 0, which equals 0, 0, called the zero vector, has zero length and no direction. In other words, it's a dot at the origin. So that's basically the idea of a two-dimensional vector. So a couple of things. The magnitude. The magnitude or absolute value of the vector is the non-negative real number representing, again, the magnitude of the vector, which is the square root of a squared plus b squared. Remember, right now we're just talking about vectors that start at the origin. So if I am talking about vector 4, 1, then the magnitude of this vector would be the square root of 4 squared plus 1 squared, which equals the square root of 17. It's the distance formula. Magnitude is distance. The bigger the vector, the longer the vector, the larger its magnitude. The direction angle of a non-zero vector V is the smallest non-negative angle formed with the positive x-axis. I have a vector here, positive x-axis as the initial ray, and the standard representation of V as the terminal. So this theta would be my direction angle of this vector. The head minus tail rule says that if I start a vector someplace other than 0, 0, for example, if I start at the point 2, 2, and go to the point 7, 5, then this vector would be vector 5 minus 2, x minus x, 7 minus 2, 5 minus 2, or the vector 5, 3. And if I put that vector at the origin and drew a vector of the same direction and magnitude, it would end up at the point 5, 3. Okay? So just some notation, some definitions, etc. So let's do some work here. Let's find the magnitude and the direction angle of vector V, which is going to be given -1 root 3. So first let's draw it. -1 root 3, somewhere about there. And we want, first of all, the magnitude. So magnitude of vector V would be the square root of -1 squared plus root 3 squared, which would then be the square root of 4, which is 2. So the magnitude is 2. The direction angle. Okay, so going back to our trig, remember that cosine is r over x, and sine is r over y. Sorry. So cos of theta is going to be, oh, I'm sorry, x over r. I knew that didn't feel right when I was writing it. So that's going to be negative 1/2 sine theta is going to be root 3 over 2, and the theta that meets both those conditions is 2 pi over 3, or 120 degrees. So magnitude using distance formula and finding the direction angle using our trigonometry. Let's find the component form. And the component form is our A, B of a vector with a magnitude of 3 and a direction angle of 40 degrees. So let's draw it first, something like this. If that's 3 units, then this is 40 degrees. So I need to find out what point I have here, or what my AB is. So using some trigonometry again, I know that x equals r cos theta. So x is 3 times the cosine of 40 degrees. Y equals r sine theta. So y equals 3 times the sine of 40 degrees. So my vector is 3 cos 40, comma 3 sine 40. And you can put that into a calculator and get a decimal value as well. Okay, so some pretty easy stuff: magnitude, direction angle, using our absolute distance formula and trigonometry. Okay, vector addition and scalar multiplication. If we have two vectors, u and v, and k is some real number or scalar, the sum, or the result of two vectors u and v being added together, is simply add their first components and add their second components. The product, k, we just distribute. It's k times each component. And the opposite of a vector v is negative v, or negative 1 times v. So vector subtraction is u minus v. We write it as u plus negative v. So again, some other simple definitions. Couple of ways to write this. If I have vector u, actually, let me see if I'm going to do that now, or oh yeah, let's go ahead and do this. I'm sorry. So when we're adding vectors, if this is vector u and this is vector v, there are two ways to think about this. One, I can complete this by drawing a parallelogram and drawing a vector at the same angle as v for the same length, and the same for u. And then u plus v is the diagonal of that parallelogram. The other way is to draw vector u and then to draw vector v with its tail attached. If I had done that more to scale, so if this is u and this is v, this would be u plus v. The same thing, just thinking about it a little differently. So that's adding our vectors. All right. Properties of vector operations. So several properties here: commutative property for addition, associative property, additive identity, additive inverse, zero product property, multiplicative identity, Again, this would be associative property, where A and B are numbers and U is a vector. Distributive property, and again, distributive property written the other way with two scalars and one vector, here with a scalar and two vectors. So all the properties that we normally think of apply to vectors as well. Okay, so let's do a problem here. A plane flies, not files. A plane flies due east at 500 miles per hour. It encounters a 10 mile per hour tailwind acting 60 degrees north of east. 60 degrees north of east means that this is east, here's north, so 60 degrees, 60 degrees north of east would be like that. Okay, the plane holds a compass heading of due east. Find the new speed and direction of the plane. So the first thing we need is a vector for the velocity of the plane before the headwind. So I'm going to call that u, and that would be 500, 0. My v vector is going to be for the tailwind. So this is the plane, this is the tailwind. And the vector for my tailwind is going to be 70. That's my magnitude. So the length here was 70. 70 cos 60 degrees and 70 sine 60 degrees. Another way of writing this would be 35 root 3. So if I want to find the new speed, I am going to add these components together. U plus V will be 500 plus 35, and 0 plus 35 root 3. So this is going to be my 535, and 35 root 3. So that's my new vector to find the magnitude or speed. The magnitude of u plus v will be the square root of 535 squared plus 35 root 3 squared, which is approximately, using a calculator, 538.4 as my new speed. So you notice that the tailwind has added some speed to my plane. Now the new direction, I need to find a new theta. Theta here is going to be, again, y over x, which is approximately 6.5 degrees. So instead of flying due east, do it down here bigger, instead of flying due east at 500 miles per hour, oh, that should have been a 10 mile per hour. Why did I say 70? That should be 10. Let me see if the rest of my numbers are right. I did this earlier. 10 sine, I have to change degrees. 10 sine 60 Yeah, I think we're okay. I will double check. Let me pause for a second. Okay, yeah, those should have been 10. I'm sorry about that. But the rest of my numbers I think are okay. Okay, so my direction angle, instead of flying at 500 miles per hour due east, the fact that a 10 small vector at 60 degrees changes me to a little bit larger vector flying at a little bit higher speed. So if I add my tailwind vector to my original plane vector, I get my resultant vector, which is a faster speed at a small angle. All right. Sorry about the confusion there. So let's go on and look at some things, because this has all just been vector work, trig work, that we haven't applied any calculus yet. So velocity, speed, acceleration, and direction of motion. So suppose a particle moves along a smooth curve in the plane so that its position is x of t, y of t, where x and y are differentiable functions of t. So the position vector now, r of t, is x of t comma y of t. The velocity vector, we're adding time into this, dx dt over dy dt. The particle's speed is the magnitude of vector v. Speed is the magnitude of velocity. Speed is a scalar, not a vector. Acceleration is our second derivative of our position, and the direction is the direction vector v over magnitude of v. That's creating a unit vector. All right, let's try something here. So a particle moves in the plane so that its position at any time t greater than or equal to 0 is given by sine t comma t squared 2. So let's find our position vector, which is actually given our velocity vector, which would be the derivative, so cos t comma t. Our acceleration vector, again, derivate our velocity. And our position, let's find the position at t equals 6. So the position vector will be sine 6 comma 18, plugging t into that. And I should be parentheses. We don't write this as a vector because it is, in this case, it's at a particular point in time, so it's a particular position on the graph, not a vector for all t. Our velocity at t equals 6 is cos 6 comma 6, and acceleration, you would plug in for that too. So that's not a big deal, just finding our derivatives as we did earlier, but using our implicit or derivative with respect to t. Okay, displacement and distance traveled. Suppose a particle moves along a path in the plane so that its velocity at any time t is v of t equals v sub 1 of t, v sub 2 of t. So our velocity at any given point in time, where v sub 1 and v sub 2 are integrable functions of t. So the displacement from t equals a to t equals b, we're doing an integral, is given by the vector integral of the first component, comma, the integral of the second component. The preceding vector, this one, is added to the position at time t equals a to get the position at time b. This is the displacement, so we have to add that to our original position to get our new position. So the distance traveled from t equals a to t equals b is the integral of the absolute value, which is the integral of the distance formula. All right, let's take a look at a couple of problems for this. A particle moves in the plane with velocity, oh, that's an awkward break there, sorry guys, velocity of t minus 3 pi cos of pi t, comma 2t minus pi sine of pi t at t equals 0. The particle is at the point 1, comma 5. So we want to find out, first of all, the position at t equals 4. So, displacement. We're going to first find the integral from 0 to 4 of t minus 3 pi cos pi t dt, and 0 to 4 of 2t minus pi sine pi t dt. And if you use your calculator, which you should, although it's not really that bad, we get 8/16 as my displacement. And so at t equals 4, I am at 8 plus 1, 16 plus 5, taking into account my initial position. So at t equals 4, go back to my parentheses, because I'm evaluating at a particular point, we have 9, 21. So that's the position that my particle is at after covering this distance along a vector 8/16. The total distance traveled will be the integral from 0 to 4 of my distance. So again, t minus 3 pi, cos pi t squared plus 2t minus pi sine pi t squared dt. And this is approximately 33.53. Okay, so using some of the formulas that we've just gone over and doing a few problems, we will do some more work on this obviously together, but that's it for the video.